Hi there, my name's Glenn and welcome to part 2 of my how-to guide on using the serial object with Arduino on my All About Arduino channel. So last time I left off looking at some challenges with the standard Arduino objects, particularly in relation to how we might use them in other scenarios. So we'll address that in this video, and also we'll look at ways of reusing some of that code in more complicated programs such as the noughts and crosses or tic-tac-toe game that I showcased in the first video, and we'll have a look at how that works. Okay, also if you like this video, don't forget to click the like button and also subscribe to my channel and turn on notifications so you see new content when I post it. And also leave a comment. That helps me sort of get a better feel for what people like or don't like, or what they'd like to see, or any suggestions. And so yeah, without further ado, let's get stuck into it and look at the second part of using the serial objects on Arduino. So last time I left off with the serial object readString methods and some of the challenges that are associated with using those. And so now we'll look at ways of dealing with that and create some reusable objects that work well in all environments. But let's have a quick recap first. So the first thing is, if I type something in, you can see that the LED that was blinking will stop blinking. And that's because the read string takes control of the processing, which means any other stuff that you've got going on in the background can't do anything. Also, because it has a timeout basis, if we're slow at typing, we kind of get partial inputs, and that makes it a little bit difficult to use, particularly in a putty environment. It's not such a problem with the serial monitor, but it does cause a problem if you use something else. So the other challenge we have with it is that the serial monitor manages the editing of the typing into the sentence. So what that means is that the read string doesn't need to have any support for managing things like backspace or other other things like that. So if I type in a few backspaces, you can see that the quote is in the wrong spot in that hello string, and that's because the backspaces are actually part of the string that readString returns to us. It's not handling them very elegantly at all. So if we don't type in our commands correctly and fast enough, like hello, then we can have additional problems, like we get embedded backspaces and maybe partial sentences and other things we have to manage. So as a generic solution to receiving or handling serial data, readString is not that great an option in my opinion. Okay, so how can we deal with some of those issues? Well, basically I'm going to make readString work the way that I want it to do. Now it might sound a bit tricky, but it's not going to be that hard, and we'll just step through it one step at a time. And in order to do this, I'll start using putty a bit more. So I'll start by showing you what it is that we're going to be working towards using putty. Okay, so there's putty, so COM20, 115200, and we'll start that up. Just check that's the same. And so what I'll be using on the Arduino is this program over here, and I'll just have it positioned at the help page because it's useful just to sort of see what we're getting. And you can see that the the program will have these commands, and we'll look at that once we get it up and running. So once again, 115200, and that's because we're using 115200 in our serial in the Arduino program, which is not there. Oh, there it is. Okay, and so back there's our help, so we'll see that later on. 115200 open, and we should have our session. There it is. There's our banner, which is coming out of the setup. And just to see, I can type in commands like usage, and we'll be able to see that result there, which is what we're seeing, and that it's print messages over there. So as you can see, one of the commands is echo, and optionally it can be on or off. So I'll type in echo on. It's not echoing yet because we haven't turned it on yet, but when I hit enter, we can see there's the command, and now echo should be on. So as I type things, we should be able to see them being echoed back. Also, if I make a mistake, we can use backspace, which will work, and we can show the echoes on. And then if I do a backspace there, we can see that's echoed, but that's an invalid command. So it reports that and shows us the help. So that's showing that that's worked. And then we can do things like the LED command, number 3, and then on, and lo and behold, LED 3 comes on, which looks like that's the case. And I can do LED 3 off. Now, one of the things that we're going to be doing here is we'll be collecting all of the letters as we type them into what I'm going to call a sentence. And that just makes it much easier to deal with them rather than each individual character, like dealing with an L, then an E, and then a D, or whatever, and so on. But that also creates a problem because one long sentence is very difficult to deal with if we look at the options and the variations of the commands. So you can just see with these two, there's already 5 options. So you can type help, or you can type usage, or you can type echo, you can echo on, you can type echo off. And so that's quite a lot already. And there's actually more because we could put spaces and things like that in the middle of them. And that just makes it even more complicated because you have to deal with that. So we'll look at a thing called parsing and actually break this down into the individual chunks, specifically the words. So the individual words would be things like echo, usage, LED, on, the number, and stuff like that. And so when you consider the LED command, there's actually quite a lot more variants that are possible that are valid and many more that are invalid. So I could, set number 4, I could set number 13, and you can see that they come on, and you can see LED 13's on, and sure enough, it's on. It's a bit hard to see because it's sort of behind those wires there. So I just move them out of the way, and you can see that the LED is on. If I type in LED 13 off, and then with a bit of luck, it will turn off, and there it is, it's turned off. And this can also consist of lots of variations, such as this one, and like that. And it'll still recognize and process it. So the first thing we need to do is to collect everything into a sentence, and then we'll process it. Just clean up a little bit. We won't need this anymore because that'll just interfere with our upload when we get to that. So what I'll do is start with this string program from before, because what I want to do is to keep this heartbeat in place. And so what we should see is that unlike the previous one where we're using the read string, the heartbeat won't falter when we're doing this. Because it won't have to be locked into that read string until the timeout occurs. So when we get this working, we should see the heartbeat just going and it won't falter at all. And so the first thing we're going to do is read in the character. So if there's a character available, I'm just going to read it. The next thing I'm going to do is work out what we want to do with it. And there's 3 main things that we want to do. So I'll just put some pseudocode in there for now, and we'll fill that in shortly. So if we get a new line, I want to process the input. Otherwise, if it's a backspace, we want to remove a character. Otherwise, we'll just accumulate that character into the buffer. So that's anything else that we type in. That's not a new line or a backspace. We'll just accumulate it, but for now, I just print it out. So how do we do these two? Obviously, we're going to do some sort of a test. So if ch equals, because we're doing a comparison, and we want to check like that. So we want to check for something like that. So is it a new line? I'll just put that as a comment there for later on so we can remember what we're doing. And then the same here. So if the character is a backspace, now that's not valid because that's not a single character string. Unlike that, you can see we get the syntax highlighting showing that it's recognizing a single character string. So how do we test for these? Well, one thing we could do is we could use the hexadecimal codes from the test string that we looked at before. But C also recognizes some things called escape sequences, which are special characters such as the new line and the backspace. And so what it means by escape sequences is we have these normal characters like these, like an R or a T or whatever, and we put a backslash in front of it. And that changes the meaning from the regular character, from like a plain old F, to something special, or a plain old N to something special, or in this case, a new line, or a plain old R, a carriage return. So even though it looks like two characters, it is actually interpreted as one and recognized by the compiler. And we can see that where we have this, it's not recognized because that's two characters. So if we get rid of that as one character, it's certainly recognizing as a proper character. But if I put that backslash in front, then it recognizes as a single character. So that's a valid comparison now, and that's a valid single character. So with carriage return or a line feed, so either of those could be an end of line, and they correspond to what's in the serial monitor. Specifically, so I just arrange it so I can see everything. Yeah. So those things correspond to these settings in the serial monitor. It's currently no line ending. We could choose new line, which would be the backslash n. We could choose carriage return, which would be the backslash r. Or we could choose both of them, in which case we get the backslash n and the backslash r. I'm not sure which order that would come in, but we do need to allow for both. So we just put that in. So if it's a carriage, if the character's a new line or it's a return, then we want to process the input. Otherwise, if it's a backspace, for now, what I'll do is just print a message saying that we've seen a backspace. And I need to come back and fix that comparison up a bit later. The other thing is I'll just prepare this function. I think I'll put it here. So let's do something simple for now just to see that it's working. Now, we're not limited to those special symbols in a context like this. We can actually use them anywhere a regular character is valid. So I could put them in here, for example, and this would be a convenient way to put a few extra blank lines around this message here. Now, I'm still going to get the new line that the print line will come produce, because that is a print line. So we should get 2 lines at the end of it as well. So we should get a couple of blank lines around that message. So let's try uploading this. I'll just save it as something else first. I think serial handler. Yeah, that's a good name. Okay, let's give it a try. So I want to print something. It doesn't make much sense to print nothing. Oh, and we're doing Arduino C++, not Java. Not that that's Java either, but it's much closer to Java than it was to C++. Okay, that looks better. There's our banner, and I can type in some characters like hello, and we can see that's being echoed courtesy of that print there. So we didn't get any processing messages, and the reason for that is because we have no line ending. And that was from leftover from before. So let's choose any of these. I think I'll choose this one to see what happens. And type in there. And we can see that the data is echoed, and we've got 2 processing messages. And that's because we're sending both a new line and a carriage return. So what that means is that this is being true for the which order they come in, but once for the new line and once for the carriage return. So I can fix that by just choosing one only. So I'll choose new line, type in hello, and now we can see we've got the data being echoed, and we've only got one processing. If I choose carriage return, the same thing should happen. Maybe put something else, and you can see we've just got one of them. If I go back to here, then I should get 2 processing messages again. So we're going to need to deal with that a little bit better later on, but for now, let's have a look at putty. So it's still comp20. There's our banner. And so what we're looking for, first of all, is that the heartbeat doesn't stop. So we never get suspended by the read string, and sure enough, it's still blinking. We're getting the echo back, seeing the processing message, but we didn't see the backspace. I'll come back to the backspace thing shortly. Okay, so the next thing I'm going to do is to capture all of this input into a sentence. And what I want to be able to ultimately do is, in this processing input message, actually output the data that's been typed in. So in order to do that, I need a couple of things. So one is an input buffer into which the characters will be stored. And the input buffer is simply a character array. And so we'll set it, I think, to 80. We do have to specify the size because we're declaring an array and not initializing it. And this is contrast to the way the string works, where it sort of gets memory as it needs it. In this case, we're allocating it beforehand. And by getting memory dynamically, that can cause some problems in other areas. And it depends upon the situation. It's a bit complicated. So this is sort of part of the doing it in a better way by not using the string. Now, the other thing that we need is somewhere to track where the characters that we're reading in or storing in the buffer will be going next. And so that buff pointer will be a pointer into the in buffer, and we'll start off at the 0, at the very top of it. Now, to output it, when I set it up correctly, all I need to do is print it. And I'll just put some quotes around it. We can sort of see the content or the exact content of it. So we'll print the word processing with a quote, and then the buffer, and then a closing quote, then a new line from the print line. All right. So the next thing we need to do is we need to collect the characters into the buffer. So I'll continue printing them for now, but what I want to do is just store them in, or store it into the array as indexed by the buffer pointer. So just like that. And then because we've stored the character, we need to count it. We need to account for it and basically put the buff pointer one position further. And the last thing I'm going to do is, which is required for this to work properly, is to null terminate it. And so we can do that is like this. And so this \0 is another one of these special escaped characters that's not actually shown there, but it matches this one here, \NNNN. And that's a code unit where the NNN is an octal digit, and in this case, \0, I've just put 10, and so that will make it a null character. So every C string like these that are enclosed by double quotes, such as these ones, they will all have a \0 at the end of them. Now, it's not those single character ones, but the regular strings, they will have a \0 or a null character at the end of it. And that null or that 0 byte would be following the E in this backspace example. And so that's a convention in C, and a lot of functions will understand and recognize that and expect that null terminator, and print is one of those. And so what the print is doing, we give it the pointer to our buffer, and it'll just output characters one at a time, and it'll just keep doing that until it finds this null byte at the end of it, and that's when it will stop and return. The other thing that we want to do is reset the buffer when we've processed it. So just can do that like this. Just reset the counter or the pointer to 0, and then null terminate it. So basically the null will be at the beginning of the buffer, and therefore it will be an empty string effectively. Okay, so just get rid of that. Try uploading it. Okay, so I'll use the serial monitor just in the beginning. Okay, so there's our banner. So we've got new line and character return. So hello, and we can see now we've got the processing and we've got the hello, and it's exactly as the code implies there. And we've got this one with the empty string. That's because we've reset the buffer after processing the new line or carriage return, whichever comes first. And then we got the other one, and so we process it again, but it's an empty string, and so we get the just the two quotes all by itself. Now, if I change that to a new line, then we only get one of those, and we can see it's got the output. So let's just see how that goes with putty. The other thing to note is the LED's been blinking the whole time. It's never faulted. Okay, so do that again. We're only getting one. That's because putty's only sending a single one of those line feed, one of those new line characters, probably the line feed. Okay, so one of the problems, we're not dealing with a backspace yet. So if I type a backspace, it should. Oh, what's going on there? Oh, that's because it's recording it, not processing it, and that's because we don't have the correct escape sequence there. So probably what's happening there is it's comparing it to a B. So if I type in bad, then no, so I'm not sure what's happening there. I thought it might have matched a B, but it doesn't. So anyway, we'll fix this up next. And the other problem that we have is that we could exceed this buffer size, but let's deal with the backspace first. So refer back to here. We can see a backspace is that one, \B. So we'll just put a backslash in there. So if we put that \B in there, now it should work a bit better. So now we should be able to see the the backspace word being printed. So I need to close that so we don't get the upload error. Now I'm not going to be able to generate backslashes from the serial monitor, so I'll have to use putty. So I'll just set up another one ready to go. Okay, there it is. So there's our banner. So type in some words. If I type in hello, and if I hit the backspace key, then we get that backspace message. So that's not that helpful. But if I hit backspace, we get that message again. So at least we can see that it's working. So the next thing we need to do is actually make it work properly. So close that. So instead of doing that, all I need to do is remove or decrement the pointer, so subtract one from it. But I also need to bring forward the null terminator. So I'll put the null in at the new location. And that should be enough. Let's give that a shot. Okay, so HEL, so I've got 3 L's and then an O, one backspace, another backspace, another backspace, another backspace, and we have HE, which is what we'd be expecting. So that's great. The user interface is not that nice though, because we're not sort of getting rid of those characters from the display. So how can we fix that? Well, let's see. So we could just do this and echo that character back, that backspace character back, and see what happens. It's a little bit of a hassle to do putty all the time, opening and closing it, but unfortunately we have to do that to allow the upload, and of course we need to use putty to test the backspace. So okay, here we go. So HE, lots of L's, so backspace, and you can see the cursor is actually moving backwards. So we still have the problem that the characters are visible. So how can we get rid of those? Well, basically output a space and another backspace. So the space will overwrite the character. The terminator overwrites the character under the cursor. And so we can just do that in our code, and it'll happen really quickly, and it'll appear like the characters are being deleted. So yeah, so we just got an H, so that looks reasonable. So what I can do that is to output the space, because we've just echoed the backspace character we read, and then move the cursor back one more time. So that's how we do it, and we use the special character in the string like we used the new liners before. All right, so indeed, we can just simply do it like this. Just have a hard-coded string, and so we'll give that a try. And once again, the LED has been blinking flawlessly, apart from when we upload, of course, or reset the Arduino. Okay, so HELL, few L's, and backspace, and we can see now that the characters are being removed, and it's sort of what we expect it to be. So that's working quite well. Now this will still work with a serial monitor, even though it can't generate the backspace, but that just means we're not executing that portion of the code. If there were any backspaces, it's being handled inside the serial monitor, and we wouldn't see that in our Arduino code. So it's just going to work the same way, and there it is, you see the hello coming up. Okay, so that's working pretty good. We still have a couple of potential problems to do with the overflowing the buffer. It'd be very easy if we did type in too much. So we need to put some limits on there. We could also underflow here. We don't want to go past 0 to -1 and things like that. So we'll deal with that. I'll put the code in first. So what I'll have is if the buffer pointer is more than 0, so there is something in the buffer, then we'll do that stuff. Otherwise, we won't do anything. But for debugging, I'll just output this message so we can see that it's working. But we wouldn't normally have this in our code, because that'll just make the interactions very messy. So similarly here, for when we're recording the characters, if there's space available in the buffer, then we'll do that stuff. Otherwise, we'll just print an overflow message. Okay, so how do we test for, is there space available? So again, it's the buffer pointer, and we want to make sure it's less than the buffer size. Actually, I think less than or equal to. Probably, can we get away with that? Buffer size. Yeah, I think that's going to work. So if the buffer pointer is less than the buffer size, do we need -1 to allow for the trailing null? Yeah, I think that's right. If the buffer pointer is less than the buffer size -1 to allow for the extra trailing space, that's why we need for that. Otherwise, we might put the trailing null past the end of the buffer, and that would be a problem. So let's test that by making this a bit smaller, so it's a bit more easier to get into the overflow situation. We'll see how it goes. I'll just use the serial monitor initially, and then once we get it working, then we'll go through the hoops to try it with putty. Okay, so if I type in 9 characters, that should be okay. So we get the processing message. If I type in the 10th character, that's 9, one more. So yeah, so we can see there's the overflow message. All right, so let's try that with putty. In putty, it'll be a bit more immediate, because we're actually getting the characters as we key them, rather than the serial monitor which accumulates them. Okay, so that's 9. So 9, and so that's fine. 8, 9, and then one more. So this should give us the overflow straight away. Yep. And each key I press is going to cause that, because we've already reached the maximum. If I hit enter, then we get processing with those 9. So that's good. Now if I do 1, 2, 3, do backspace, that's fine. Another one, that's fine. Another backspace, that's fine. But if I hit one more backspace, we currently have the empty string, but if I hit one more, then we should get the underflow, and indeed we do, and that'll keep happening until we type stuff in again. And so if I type more stuff in and rub it out, same thing happens. So we've kind of guarded our buffer to prevent it from buffer pointer from going negative or overflow, and that's very important because you need to sort of think about what would happen if we did go past the end or the beginning of the buffer. So if we went past 10, what would happen? We'll probably overwrite that, or randomly overwriting something else. Same if we went negative, it would just randomly overwrite something that we don't know what that is, and that's undesirable. We certainly don't want to be overwriting the -1th element of the array. It could be the in buffer pointer, so the buffer pointer, it really depends upon where the compiler puts those things and what it puts around it. So it's really undesirable and don't want to do that. So it's important to guard it. So I just reset that to 80, so you have a decent size. And you pick those numbers based upon, making sure you have enough capacity for the longest string that you're expecting to get. Okay, so we've got protection for accumulating the characters into the sentence. And so the next thing we're going to do is take all of this, and then we'll be parsing that input. So we'll take a command like that, and we'll process it and look at the individual words and work out how to deal with that. And so as I said, there's quite a few variants, and we'll sort of cater for that. Oh, I've still got the 10 character buffer. So anyway, we'll look at this next. So there's two major parts to parsing. Actually, there's more, but we'll only look at two. One is lexical analysis or tokenization, and the other one is syntactical analysis, which is applying rules of grammar. So that's basically looking at the sentence structure, and lexical analysis is sort of breaking a sentence up into manageable chunks or tokens that we can deal with in a more manageable format. So we build a method that helps with both of those. Both of them will be fairly simple. They definitely won't be as sophisticated as what's used in the compiler or something like that. And so, as I've been saying, the process is a little bit easier if we collect all of our input into a unit of work, and I've been calling that a sentence. So let's consider this simple example. When we do the lexical analysis or identify the tokens, we'll identify each one of these things that I've put little yellow boxes around. Now, in this scenario, I'm not going to deal with, I'm not going to bother with punctuation characters. I mean, typically you'd want them to be separate symbols or tokens, but I'm going to keep it fairly simple and not bother with any punctuation. And I'm just going to simplistically look at things that are separated by spaces, which means that day and comma would be one like token, and typically you wouldn't want that. So I won't worry about punctuation characters. I just look at words or tokens that are separated by white space. Okay, so look at this particular example, LED 6 on. That's one of the examples I've been using in previous examples, LED 6 on. And once we've identified the tokens, then we need to check the syntax that it's what we're expecting. So I've typed a few examples previously, and those examples follow this diagram, which I think is called a railroad track diagram or something like that. It's sort of like railroad tracks with the sidings and different paths that you can go, and that sort of defines what the grammar is or the complete language. So we're working towards that. And while it sounds complicated in the code, it'll be fairly straightforward, or hopefully it'll appear straightforward to you and understand it. So here's the examples. There's usage and help, which I've used a few times. They're fairly easy to process. You just look at the one word. But then there's a couple of structures, echo and LED, and they're defined down here below the diagram. It says the echo, and so we can type echo with nothing, or we can type with echo or options on or off, and then there's LED pin and high, low, on or off. There's no options other than the choice of that last word. And so that's what we'll do. I'll start with identifying what the words are or the tokens are that are circled there. and we'll then apply the rules of this diagram and action the command based upon that, and hopefully we'll see LED 6 turn on. So I'll continue on with this program where we're collecting things nicely into a buffer and process it, and so we'll focus on this function here. So I'll just save that as something else so I can go back if need be. So as I was saying, we'll dispense with this because that's just going to get in the way. We don't need that anymore. And also maybe get rid of that. That's just taking up space, not doing anything anymore. And now we've just got our character accumulation handling. What I might do, because I know I'm going to do this, I'll just set all of my pins to output. Right, so all of the pins are set to output. And so the pins that I'm setting to output will basically this entire row here, 2 through 13. Now I've deliberately skipped 0 and 1 because they're the serial they're the serial pins for the Uno, and so we can't use, and we'll look at this a little bit further later in the video. You can use them, we have to be a little bit careful, but I won't bother with them. Now we can also use the ones over here. I won't bother with them. Now for this board, for Uno, the IDs will be 14, 15, 16 and so on. But that only applies to an Uno. If they were a different board like a Mega, then the numbers will be different. So I'm just going to ignore those. You can experiment with that if you like. Okay, so we set our pins to output. So that's ready to go. So now all we need to do is process our input. So once we've got our sentence, I'll just simply print the tokens that we've identified. And the way we can do that, actually, first, I think what I might do is put another little guard in here because I don't think it's a good idea to try and tokenize an empty string. So let's just make sure that we actually do have some tokens. If we don't have any input, then I'll just simply print a message and return. Okay, so I think I moved that down to there. That makes it a bit cleaner. And yep, that's good. So ready to go and start tokenizing. Now, the next thing we're going to need is to identify the delimiters that we're going to use to separate our tokens. And I think I'll use space, and actually I think I'll use tab as well just to see how that goes for now. Maybe not. Yeah, I'll use tab as well, so just show a bit of flexibility. Normally I'd just use a space, but let's add a tab which is \T. It's a horizontal tab as we refer back to our chart. So let's see how that goes. So they're the delimiters I'm going to use to separate the words out. Now the C runtime library provides us with a nice helper function to tokenize our input, and that function is called strtoke. But it is kind of destructive in that it alters the string that you give it. It basically puts nulls where the tokens are, so it splits it up. And so it basically breaks our input buffer. Now, if you want to keep an original copy of your input, you do need to copy it off somewhere else. And I do want to make a copy of it because I want to have the ability to say invalid input and then echo back what was typed in. So I can't afford to have the strtoke break it up because it'll alter the format of it, especially the things like lots of extra backspaces and things like that. So what I'll do is I'll copy it into a work buffer, and obviously we need to declare that. I think I'll just put that here. So now we've got this working copy, and I declare that to be the same size as our original buffer. And so the next thing I need to do is to create a pointer to the tokens that are going to come out. So what happens is when we proceed, we'll get a pointer to the L, then we get a pointer to the 6, and we get a pointer to the O, and that'll be the 3 tokens that we'll be getting out of it. That's what the strtoke does. So we have to use a loop. So let's start strtoke. It takes two parameters. Initially, you provide it with the input buffer and the delimiters. And pretty much all we do is proceed through a loop. I'll just create another variable as a counter so we see how many tokens we get, but we'll also use that later when we remember the tokens. So while the token is valid, all we want to do is print it. Now the strtoke will null terminate the token that it returns, which, as I said, that's where the destructive part of the buffer is. So where there was a space, it'll replace it with the space. So it'll replace the space with a null. So null being one of those. So that's why the serial print will still work. We don't want star token because that's already a pointer. We don't want to dereference it. If I did star, that would actually just print the first character, so it's not terribly useful, at least not in this case. So just close our quote. So what we should see is the token 0 would be like LED or whatever it is, and then token 1 would be 6, and token 2 would be on or off, or whatever. So we need to generate the second word, or the subsequent word. So we call strtoke again, but this time the first parameter is null, which means use the previous buffer, so MSG work, or basically continue on from where you left off. If we gave it a new one, then it'll reset and start over. We don't want that. We want it to continue with what it was using previously. And finally, just increment the token ID, so we count it. Now, if there is another token, then token will get the pointer to that token. So like for the second word, we'll get the 6, then the third word will get the on, and so on. And when it runs out or gets the end of our input, then token will be null, and so the loop will finish. All right, so just print that message. I think that's good enough. I don't think we need anything extra for that. Let's give it a try and see what happens. Now, you do actually need to include a library for these str functions, strtoke and strcopy, but in an INO file, the Arduino environment includes the necessary file for you. Okay, so we've got an error. That's one. Don't want that. What else have we got? The delimiters. And this one's wrong as well. Work buffer. All right, looks good. Let's start the serial monitor and give it a try. So we'll try that example, LED 6 on, and it didn't work. Well, why didn't it work? Oh, that's because the delimiters is a string, not a character. So that means a single character. We need to make it a pointer to a string. Hopefully that'll fix it. We'll soon find out. And there we have it. So you can see it's identified those words. It's also removed all of the spaces. And so it's handled that nicely. And it also works if we put in multiple spaces as well. So it does the same thing. So there's some nice functionality in that strtoke function that helps us tokenize our string and gives us those individual words which you can process in the next step. So let's try it with putty. It obviously should work, so we've not changed anything in relation to the accumulation of characters, but just to be sure. And you can see we've got the same 3 tokens. So similarly, if I type in a few extra spaces, get the same thing, which is what we'd expect. If I typed in usage, just get the 1 token. So if I type in some mistakes, let's use the backspace should work. And it looks like it does because we've dealt with those sorts of issues earlier. Oops, I should have tested the tab, so we'll just restart that and try the tab. Okay, so LED space 6 on, so that's the same. LED tab 6 tab off. And so it's recognized both of those. If I tried to use something else like a random character, we haven't specified those as the symbol, and so, sorry, we haven't specified this on a delimiter, so we get those recognized as tokens, and that would be undesirable. And you can sort of see how the second token, or number 2 there, it's attached the 6 to the semicolon, so that makes it a little bit more difficult to process. We could do more with it, but again, just to keep it simple, we'll just not worry about any punctuation or anything like that, and we'll just look at spaces and maybe tabs. Right, so what can we do next? Okay, so just quickly go back to the theory. So what we've done is we've done the lexical analysis and we've picked out our tokens. So the next thing we need to do is to take those tokens and perform the syntactic analysis, or the grammar rules. And so essentially that's applying this diagram over here. Now, to do that, it'll be much easier if we remember what the tokens are and then we pass that to another function. So what I'll do is create another array which will track our tokens. So what I'll do is remember the token in the array, indexed by a token ID, and then we'll use that set of words for applying the syntax. All right, so we'll have a character array of tokens, and we'll create that to be max tokens. I think we'll set that to about 10. That should be plenty. That's more than enough for what we want to do. Any beyond that, we'll just discard the extra ones. And we'll deal with the tracking of it here. So that needs to be an array of pointers to the strings. So that's the array, which is max tokens in size, and each element is a pointer to a string of characters. So a token is a pointer to a character string, so it matches that, and so there'll be an array of 10 of those. Okay, so all I need to do here is remember the token. Just remember it, and that's it. Now take this stuff out and move it down here, and just simply print out the ones that we've remembered. So just change that to reference the array. So we should get the same result as we step through the array of tokens that we've remembered up to the token ID. So the token ID would be the count. So if I starting at 0 and going up to 1 less than the token ID, then it'll print out the correct number of tokens. I'll also move this, so that just to prove that it's coming out of there after it's been tokenized. Should be good enough. Now I won't bother with checking the maximum token ID. You should do that. You should put that guard in there for the same reasons discussed before. I'll leave that as an exercise for you. We'll just keep moving on. It's basically the same as before, just different values, that's all. All right, so let E6 on, and so we can see as before. So echo the input, then we do the tokenization, and then we print it out here, just to show that it has actually worked. I just changed the message. Okay, same command, and you can see we've got the colon equals now. So it's clearly come out from here, and remembered the array. So the last thing we want to do here is to process them. So we could process them here. I like to have a separate function. So just separate the responsibilities. It really doesn't matter. It just makes it a little bit neater, I think, to have it in a separate function. But we want to pass the tokens. We want to pass the number of tokens. And finally, we want to pass our input buffer. So if we have a situation where the syntax is invalid, then we can actually echo back exactly what was typed in. So process tokens. Just move that up there. Okay, so let's set up our process tokens function. With our in buff, I could declare it the same way as I've done there. I won't, because I don't necessarily want to restrict the size to something. I'll just accept an arbitrary length string, so I'll just declare it as a pointer to a characters. So that means I could deal with varying sizes, for example, without having to worry too much about that. Now this one, I'll rename it to token count, because it's actually a count of tokens when we get to here. Whereas it's defined as an integer. Oh, there it is, int token ID. And I'll declare this the same way. Char star tokens, so pointers to strings, and basically I'm going to make it an open-ended array, again, so it can deal with different sizes if we needed to. So I could, just a matter of interest, I'll take that out of there and put that there and show that it's passing it correctly to this function. Process tokens, I'll just change that. So this is wrong. That's now token count. I is fine. I less than token count. So that should be fine. Let's try it out and see what happens. I'm going to recall our string and change our message process tokens just to getting the 3 tokens. And so, oh, hang on. That's 6. That should be LED, not 6. That's a problem. I just noticed that. It's been like that for a while. So obviously we're not remembering our tokens correctly. We're losing the first word. Why is that? That's because doing this in the wrong order. What we need to do is remember the first token that was generated before we start the loop, and then work out the next one and remember that for the next time around, assuming it's not null. So the first one would be LED, and we remember that. Then we increment it and get the next one. So the next one will be 6, which you remember, and so on. So this one should be a bit better. I assume all of you noticed that earlier and was shouting at the screen, oh, it's wrong, it's wrong. Anyway, better we figured it out. Let me know in the comments if you saw the mistake. Okay, so it's working better now. I've got the LED 6 and on. And yeah, so we've got the equals greater than. So it's coming out of the function. So we're getting our tokens passed correctly. So that's just a matter of looking at those. So let's start that now. So we can do that with another if. And so what I'll do is use a string comparison. You might be tempted to do something like this. I don't know, LED. And then do something with that. That's not going to work. It's to do with C manages pointers. So this is a pointer to a string that's been defined separately to that. And even though it might have the same letters, it's not going to be equal. So it doesn't work like that. Now this would work if tokens was a string object, but it's not. So we have to use a C function, and it looks like this. So we just compare our first token, and then this will return a value. So if it returns a value 0, then that means it's equal. So it checks the contents. So I just set all of these up. Okay, so that's our syntax. So I've got the base words. So usage, help, echo, and LED. Or almost. So help, echo, and the LED commands first. So what we're doing is just looking at the first token and saying, which one of these is, or which branch are we going to go down in this one? And then we'll just break that down further and drill in as we need to. So let's put another print here. What I might do is copy that from somewhere else. Because I'm going to reuse that a few times, I'll put it into its own function. And then lastly, assuming we don't have any recognizable input, then we'll print up an error message. Now, so this is where we want to have the unmodified string. So that's the original input that was made on the by the user, and so we'd echo that back. So what we're doing is printing out the tokens as before, then we'll work out this branch, and we'll print out an appropriate message. And if we do find the usage, we'll call this function, which will output a much more useful message. Otherwise, we'll say it's an invalid command and then echo back the content. And we could also call usage here as well. Okay, so let's give that a try. Okay, so let's try blah, blah, blah. And as we'd expect, it's none of those. So we get this invalid command path and we get the helpful message. All right, let's try usage. And this time we just get the usage information. We don't get the invalid command, so it's worked correctly there. If I try echo, I could put anything here because we're not checking anything else yet. And we get all the tokens and LED command. Oh, that's not right because the message is wrong. But if I said LED blah, 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 then we get LED command. So, I mean, that is actually working, but we'll see that's working fine next time. We also have a problem. But if I set LED with a capital L, then we get this invalid command. And the reason for that is because strCompare is case sensitive. So because that capital L doesn't match the lowercase l, that's not equal. So there is actually a case insensitive version, strCaseCompare. Now, for some reason, the IDE doesn't highlight that. It is a standard library function, and it is actually documented in the AVR libc reference pages. I do seem to recall from earlier in my career there was an strICompare, where I means ignore case, but that one doesn't seem to work. So strCaseCompare is the case-insensitive comparison that we'll use. All right, so let's try that. We fixed the message for the echo. Echo on, and so we've got and it's got the echo command. Try LED 6 on, got the LED command. Now if I type in capital letters, so echo, and we've got the echo command, LED on. So yeah, that's working. It's recognizing the case correctly, or ignoring the case correctly, I guess I should say. So I've just been talking about pointers, and this token was a pointer, and also I created an array of them. And so I guess the question is, what are pointers? Some people seem to be able to just follow them naturally, others seem to be confounded by them. So I don't want to turn this into a lesson about pointers, but we'll just briefly look at it to make sure you're all on the same page. So far in our program, we've identified tokens and done a little bit of message processing or message handling for usage, help, echo, and LED. Next, we'll add this part. But first of all, let's look at the pointers. So quite simply, a pointer, as its name implies, it's something that will point to something else. In this case, we're going to set up pointers that point to character strings, or what we call the tokens. Later, I'll look at a different couple of pointers, one for a function and then one also for the serial object. So I'll cover that when I get to it. But for now, we'll just look at what we've done so far with the tokens. So let's again consider this this input LED 6 and on. And so what happens is, as we tokenize it with this strToke function, we're given a pointer to each of the words that it finds, or each of the tokens that it finds. And the pointer is, the pointer is the token, and it's a pointer, which is what the asterisk means, and it's a pointer to something that's of type character. And so each time we call this strToke, we get the next pointer value. So the first time we call it, the token will point to this first token, LED. When we call it again, we get the 6, and note that we've lost the pointer to LED because the thing can only point to one thing at a time. And when we call it the third time, we get a pointer back to this on keyword. And when we call it the final time, then it returns null, and that's when we know that we're done. There's no more tokens for it to process. That's great, and we initially did that where we printed out the value of the token each time, and we saw that it printed these 3 strings, or whatever the words were that we entered in the sentence. So that's great, but once we've got the tokens, we want to capture them and process them in some way. So a pointer is a data type like anything else. Just like anything else where we can create an array of, like an array of integers, we can also create an array of pointers. So our token is a single pointer that points to one thing. But if I put these square brackets after it and an array size, then we're actually allocating a box of tokens that we can use for whatever reason we like. So if I declare that, which is what we had in our source code, there it is there. Then essentially we get a little box with 10 spaces in it, and each one of those spaces is a pointer to a character. So now as we process our input, back to this, it's the same as before. As strToke gives us each pointer, what I'll do is I'll take that and just remember it in this array. So we're able to remember up to 10 keywords. So we transfer that into the array, and now this first element in our array, so element 0, is pointing to the LED. If you're not familiar with arrays, I did cover that in an earlier video relating to post starter kit, and there's some illustrations in more detail about what an array is and what these numbers mean. So I suggest you have a look at that. But for now, just take it that tokens 0 is this LED keyword. So if we call strToke again, we'll get the pointer to the 6 as before, and again we'll just update that into the array. And so now we have this first element, or element number 1, which is actually the second element, we point to the 6th word. And again, now our token points to the word on. We push that into our array, and that's at element number 2. And then if we call it again, then basically we get a null, and so that's it. We know that we're done. Back 1, so you can see that, and there's the code. And that's what this while loop is doing. So we do the strToke to get the first one out. Then we store that in index by token ID, which initially starts at 0. That's how this one gets to point to here. then we increment it, so now it's a 1, we get the next token, and we basically keep doing that until we get the null, which is after we've processed this last one. But after we've done the LED, we get the number 6, so our token will be 1. That gets stored in this element number 1. Then we increment it, so now it's 2. Pull it again, we get the keyword on, and it's in number 2. And that's how we got the output that we saw earlier. I'll just run that again. Yep, serial monitor. There's our serial monitor. If I type in LED 6 on, then there we are. So we have 0 is LED, number 1 is 6, and number 2 is on, and that's it. And then also you see we have this LED command output. That is coming from this process tokens function, which is just up here. And of course, that's where the output is generated. It's 0 LED and so on. And then we're just checking tokens 0 to see if it's LED or if it's echo or if it's usage or help. And then we take an appropriate action. So if I tried echo on, then you can see we have the 2 tokens, so echo and on, and see that's an echo command by virtue of that. That's as simple as that. Now to go back to doing the grammar, all we need to start doing is looking at the next sets of tokens in our array. So to get the pin, we would look at element number 1. To get the high, low, on or off, we'd look at element number 2. If it was the echo command, then we would look at element number 2 to get the on or the off. We'd also check the number of elements that have been passed in our array. So how many of these things have been populated. So how many of these have been populated? And that's how we'll do the next steps. Okay, so let's crack on and see if we can get some LEDs turning on. All right, so now that we've processed our sentence, we've pulled out our tokens and we've saved our pointers to them, let's process them. Okay, so I'll start with the echo command because that's the simplest. And what I'll do is I'll just do something in here to deal with it. And the first one I'm going to cater for, I'll just go back. Is the no parameter condition. So what we can do to deal with that is just simply looking at the number of tokens, which is this one here, token count. I call that. Okay, so I don't have anything to do with echo at the moment, so we'll need to create a variable to track that. Okay, so we've dealt with the echo. So if the echo is turned on, then we will echo our messages back. Otherwise, we won't do anything. So we manage that. So I've looked at this question mark operator in a few other times. You can Google it. It's called the ternary operator because it has 3 parts. But basically, it's like an if statement that returns a value. So if the echo is on, I'll return the word on. Otherwise, I'll return the word off. So we should get a nice message that says echo on or off. Now we want to deal with the next situation. So we want to make sure that we only have 2 tokens. We can't have extra stuff hanging off the end here. Otherwise, it's an invalid command. So I'm going to say else if, do that here. Now I'm going to modify this function. And what I'm going to do is make it so it can take a couple of optional parameters. And those parameters will be an error message. And the input buffer. And we'll come back and deal with this in a minute. So there's our usage. Now, I'll just put the second one in. Now, we do have a few calls to usage that don't pass these parameters. So where's an example of one? Well, in fact, I think here's one, here's another one. So rather than going through and sort of modifying how they work, because I already only want to print out the usage information for this stuff, what I can do is initialize them with a default value. So if I don't supply them, if I don't supply those parameters, which is the case here, for example, then these will be null. So I can use that information here and say if message is not equal to null, and null is a special token that's defined in the runtime, which basically is a 0. So if the pointer for the message is to nothing, then we don't want to do this. But if it isn't nothing, in other words, there's a message such as this one, then we want to print it. And similarly, we can do the same here. So in the case of this version of calling usage, it'll output this error message. It'll output the command that we've passed it, because that's what we pass to it when we do this process input here. We give it the input buffer. There's that here, input buffer. And so we should get an echo back of the command that we typed in as we typed it in, and this message. So now we just deal with this one. And we just need to do a nested if, similar to what we already have. So another level of if. Right, so this time we want to look at the first token, or actually the second token, but index element number 1. And if that's equal to the word on, ignoring the case, then we just simply want to do echo on equals true. And then we'll do the same for off. And finally, if it's neither on or off, then we'll output that message. So let's just give that a try. I'll just use the serial monitor because it's a bit easier than firing up putty and shutting it down and things like that. All right, so there's our serial monitor. And so as before, I could just type in usage. Now notice we didn't get any of the characters echoed. This will be more apparent in the putty environment, more so than here. If I type in echo, so that's this first variant here, where we've just got one token, then we should see this message come out. And there it is, echo off. Now I can turn echo on. Now we probably won't see much in the way of a response other than our debugging messages. We can see our two tokens, and so theoretically we would have skipped this because token count is 2. Would have come down to here. We should have matched this, and now we should see echo on. So what if I said echo blah, then there it is there, echo blah. So it's echoed the characters back, and there's our tokens. The token number 2, which is this branch here, is blah. So that's it's neither on or off. So we get invalid setting for echo command, which is this message here. If I tried typing in a third one like that, even though on is a valid message, we should get this last message, invalid LED command. And so there it is. And so then the processing of the LED command is similar. Where's that? That's here. Except what I might do is, because it's a little bit more involved than this is, I might put it into its own function. And I'm just going to pass all of these parameters. So I'll borrow this like that. And that's all I need to do here. So where shall I put it? I think I put it here. And so there's our function. So process LED, we've got our array of tokens, we've got the count and the actual original input. Now this is going to have to call usage. So with INO files, it's not strictly necessary to have them in the correct order, but usually you'd want to have your functions declared before you call them in a C++ program. So the first thing I'm going to do is I'm going to make sure that we have 3 tokens, because in every variant of this, there's 3 tokens. If there's not 3 tokens, then it's not a valid command. Simple as that. And that's it. Print our message and return. Don't need to worry about that scenario anymore. So now we know that we have 3 tokens. So the next one is the pin, and we know that's got to be a number. So pin number 2 to 13. So we'll just assume that that's the case. And what I'll do is int pin number equals A2I. So A2I is a C function that converts an ASCII string to an integer. So I'll type it in first and then we'll look at the API. Okay, if we search for AVR libc, then we go to this www.nongnu.org, and then from here we can search for A2I. This is a little bit harder to read because we're actually looking at the standard library that is attached to the C compiler. And so we can see here A2I. So A2I takes a character, a pointer to a string, and it converts the initial portion of the string pointed to S to an integer representation. And so that it will assume that the string that we pass it contains characters that are digits, so 0 to 9, and then it'll return the equivalent integer value, which is what its return value is, integer. So that should give us the pin number that we type in. The next thing I'm going to do is determine what my setting is going to be. And I'm not going to give it a default value, and so I'm just going to check for these high, on, low, and off. So that will be on. So that'll be the third tokens, or the third token, which is element number 2 in the array. And so what we're looking for is that it's either on or high. And if it is, otherwise, basically we're going to do the same thing. Basically, we want to do the same thing, but we're looking for low or off. Now, if it's neither of those, so if it's neither of these or none of those 4 options, then we just want to output the error message and then return. Don't need to do anything else. Then last thing we do is validate the pin number. And so I think we said that it has to be between 2 to 13. So greater than or equal to 2, in this case, and. Right, so it's greater than or equal to 2 and less than or equal to 13. So we need an and because, for example, 15 would be greater than or equal to 2 and 1 would be less than or equal to 13. So we need it to be inside that range. So 2 is true for both of those conditions. But we want to do the reverse of that. Now, I could put here and else and then put the usage here, but take this opportunity to sort of learn a bit of negation of Boolean algebra. So what I want to do is say if it's less than 2 or it's more than 13, then we'll output our error message and return. Now I could also put that up here immediately after converting the pin number, and if you want to do that, that's fine. I've just done it down here because that's where I happened to think of it. So then the last thing we want to do is just do it. Now I think we've already set all of these to output, haven't we? Where's our setup? There it is. 2 to 13 are set to output. Yep, so that should work for all of them. We can put some print messages in there. I'll just copy and paste those. Number in setting. All right, so that should do it. Let's upload it and see what happens. Obviously, I need to pass the values, not declare the parameters. Okay, that should be better. Okay, so as before, you can see we don't have any echo, but we are receiving data from it. So I can type in the echo on command, and we can see processing echo on, and it should have now turned echo on. So if I type in usage again, you can see it's now echoing stuff back. And of course I could do echo off and so on. But the main one we want to test now is the LED command. So if I type in LED, then I should get the invalid LED command, which comes from the fact that we didn't have enough parameters. If I typed in like that, I should get the same thing, invalid LED command. So LED, and I'll do 6 and then on. And so what we should see is that one of these LEDs over here should turn on, and there it is, the yellow one. I could do LED 2 on. Oh, I mistyped the command. And so now we've got number 2 on. I could turn the internal LED on. And sure enough, it's come on. And similarly, I can turn them off. And it's gone off. So this is a fairly simple sort of command set. Obviously, you could repeat this and make it as sophisticated as you like. This is using hard coding. There's lots of other ways we can do it that are a bit more elegant, but this is good enough for most things. And as I said, if you had a much more complicated or sophisticated sort of situation, which we'll start to look at next, this is quite a useful technique for managing a project that you've sort of deployed. Because as you saw, I could just attach a Bluetooth module to the TX and the RX pins on the Arduino, and I could actually do this remotely from my PC or whatever. So it's a handy technique, and if you have like help in there, then that can also make it a bit easier because you can see the helpful commands. Okay, so I'll do one more thing with this, and the problem or the thing that I don't like about this is that I've got all this stuff sort of sprinkled through here. Now a lot of it's very generic, so particularly defining the buffer. What else? These functions like checking that the buffer pointer is greater than 0. We don't have any overflow or underflow, doing some of the echo and things like that. So I might split that out into a reusable class, and that will make it easier because I could then just copy and paste that, or the actual files. I can just copy those files into a new project without having to try and sort of pick it out of these bits of code here. Some of it will still be specific unless you want to do a more fancy method of processing the tokens. We still have to check that the first token is whatever it is that we want it to do. Maybe that can be a subject of a new video. If you'd like to see a more sophisticated and more generic version that we can sort of tuck away into a separate set of functions, just leave a comment and let me know if that's something that's of interest to you. Okay, so we'll move on and factorize this out and provide us with a structure that we can use for moving forward. Okay, so to create a buffer class, I mean, there's lots of different ways you can go about doing this, but I'm going to add 2 new files. Now, I don't know if you've noticed a little drop-down arrow here, but there's a little drop-down menu behind it, and we can do things like add a new tab. I'm going to add a file called buffer.h. And I'm going to add a second file called buffer.cpp. Now, so basically what this is going to be divided into is the code that makes up the buffer. So this is where it manages the things like the overflow and things like that. And then this buffer.h is, you'll note that's .h, which is what we sometimes include in our INO file. And that's going to define the methods that are available in the buffer. So the buffer.h is a way of linking the code or the file that wants to use it, i.e. this one, with the code that implements it. So hopefully that'll become clear as we look at it more closely. Now I'm going to start with this one. Now I'm going to copy and paste some boilerplate code in here. Now this is a conditional compiler directives. So we've already sort of seen the hash define one. And what this is doing is basically making sure it's not included twice. So what it's saying is when we compile a program, we're going to check to see if this symbol is defined. If it isn't defined, then we'll do all of this. Otherwise, we won't do anything. So it's a way of sort of avoiding duplicate definitions. It's just sort of a syntactic little trick or a workaround or a hack or even a bodge, if you prefer, to deal with that issue. This probably isn't terribly helpful, but it is a means that we can use to override the buffer size if we needed to. But I'm going to set it to 160, and that's where we're going to store our characters in there. Now, to create a C++ class, there's a keyword called class, and I'm going to call it buffer. And as per most C++ code, you put it in brackets or braces, and like this one, which is a declaration, has to be terminated with a semicolon. And then there's a couple of sections. So there's a public section and a private section. So a public section is stuff that's visible to other pieces of code. So this will be the stuff that this guy over here can see. There's also a private section, and that stuff won't be visible to this, but it will be visible to this guy. So we'll look at how that works a bit later. But there's also a protected section which is useful for more complex scenarios, like when we have things called friends. So I won't look at friends at the moment. This will be a pretty lonely sort of unfriendly class. So here we basically just find some function signatures of the operations that we want to do. So we'll need an append. And so we'll want to have the ability to add on a character that's been typed in. And I'm going to set a Boolean because I want to return a true or a false if it was successful or not. So I'm going to provide a remove method, and most of the time I'll just call remove. And so here's this default parameter. So if I just call remove and don't tell it anything else, it'll just remove one character if it can. Again, a Boolean to deal with the overflow, underflow situation. Now I'm going to have a clear function, which after we've done the processing of our input, we just want to reset the buffer. Now, sometimes people like to use the word reset, so I'm going to define that just as a convenience sort of thing. And up until now, I've been putting a semicolon after all of the method definitions. That means that I'm saying that this append function, which takes one character, will exist at some point, but not yet. And I'll define it later. In fact, I'll define it in this buffer.cpp class. With this reset one, you can also put the code in here. And so since reset is just an alias for clear, I'll just simply call clear like that. And that's done. And because it's a code block, you don't need to put a semicolon there like that. Now there's some other functions I'm going to put in here. This one returns the length of the input buffer. And this one just simply returns the characters that have been entered so far. Now in the private, this is where we put in the variables that will be sort of hidden away into the internals of this that we don't want other people playing with. So this is going to be the pointer to our buffer, which is basically the equivalent of this one, and then we'll also declare that one. And that's it for the declarations. The only other thing that we need to do over here, apart from removing all that code, is include it. Yep. So a lot of the time you might see include written like this. Both are valid. They are slightly different, and it's not terribly intuitive. But basically, this variant will search the current directory. So since this file is a tab in this project, it will find it here. This one doesn't include the current directory, it only searches the library path. So this one would cause an error saying that it can't find buffer.h. So we won't use that one, we'll use this one. Now, the next thing we need to start doing is saying, well, because we've declared some of these things over there, we don't need them to be here. I'll come back and I think clean out the rest of it later. But I will want to declare one of these buffers. So I think I'll declare it there. And that's it. That's all we need to declare it. So what I'm going to do is declare one of these, a buffer, which will be able to do all of these things. So append, remove, clear, and reset and things like that. And then implement the code. So let's actually just do that now. So one of the things that we're going to do is when we process the input, instead of doing this stuff, we'll just say in buff.clear. In fact, what I might do is copy that, or cut that. Like that. And then over here, I'll paste that temporarily. And what I'll do is put it into a function that handles it. And that's pretty much it. So now I've declared this clear function, which does those things. So it's setting buff pointer to 0, and it's setting our actual character buffer to a null character to signify the end. And those two things are defined over here, so that should work. But how does it know about these things? Well, we have to include this file. And it's also usually a good idea to include Arduino.h as well, because that'll often bring us some functionality that is unique to the Arduino environment. If you don't use anything like serial.println, which I will use for debugging, then you don't need that. But that's essentially it. So now we're on our way to building up our class. All we need to do is define these other methods. So I put them in there like that. Let's start with getLen. There is one other piece of notation, which is this. So this is what makes this method called clear associated with the buffer class, which is defined in this header. So this is a namespace. So what we're saying is in the space called buffer, define a name called clear. So that means that something else, if we had a token class, we could also have a clear for that as well, and that would be a different clear. And that's sort of how C++ works. It allows you to sort of attach methods to different objects based upon these namespaces. So I'll need to put that in front of each one of these that we're going to declare. Now this one we don't need to because we're just calling this one. This one will need it, and so will this one. And as I define them, I think I'll unindent them. So in this case, all I need to do is say return buff PTR. Okay. And then in this case, simply return the pointer to the buffer. And so that's sort of how easy it is to create these things. You just create these little snippets of code. You might feel it's a little bit wordy, but the fact that I can then just copy and paste these files and drop them into another project, and it'll work for many things from then on, that's very convenient and makes our life much easier. So these next ones are a little bit more complicated. So I sort of don't need to do this one. We've done the clear, so that's already done. So now it's just these two. And again, we have some boilerplate code we can copy from over here. So in buff.remove. Now, remember I said what I'm going to do is say if the removal is successful, I'm going to return a true or a false. So if removal is successful, then I want to do that. Else, actually, else I don't want to do anything. If someone keeps pressing backspace, I think I won't bother with doing anything. Now this stuff over here, I will extract from there and put here. Oh, I should have put the echo on in there as well. Like that. So if we have characters in the buffer, decrement our pointer, set our thing to null, otherwise sort of called it incorrectly, and I guess that's reasonable, but I'll still print this error message. And because I'm printing this error message in here for debugging, I'm using Serial, and that's why I'll need to include that. Now append will be very similar. That's this bit here. So it's not a new line, it's not a backspace, it's a character. So we'll do these things. And so I'll do the same thing. If in buff.append, so if we successfully append the character, in fact, I think we'll echo it anyway. If they've typed it, I think we'll just append it anyway. I think that's good enough. We'll just do that. So we'll append it anyway. And that's, I think, pretty much all we need to do here. Now this has used a different name. We're not going to do any echo here, but otherwise this is the same. So we'll write our character into the input buffer, we'll increase our pointer, and then we will terminate the string. And that's it. Right, so just have a final quick check. We're echoing a character, we're appending it, removing it, echoing the backspace stuff if it's successful. Processing the input. I don't think we need to change anything here. Yeah, so this all still looks fine. So just upload it and see what happens. Probably we'll get an error, but that's okay. Deal with that bridge if we come to it. Okay, so in our buffer clear, getting a message in buff was not declared in this scope. And that's because like that. Let's give that another shot. Yeah, we'll probably get some more errors still, but that's pretty far reaching. So let's give that a try and see what we end up with. Okay, so we can't just simply do that. I think we called it get message. Yeah, get message. So that'll probably be in a few different places. Okay, so Yes, I think that'll be pretty far-reaching as well. So let's try again. And so what was happening there, here, was we're trying to print this class, and the print subsystem knows nothing about that class, so it was getting a bit confused. Oh, I must have deleted the work buffer. Buff pointer equals 0. Okay, so in this case, what do we call that? Get len. So that's still line 106, that's the same one. Work buff size, okay. So what I can do is, because I've declared buffer size here, I can just simply reuse that so it'll match. So where is that? Work buff, there it is, like that. Are there any more of those? No, let's try again. And that looks like the last one. So this one makes that problem a little bit clearer. Can't convert buffer, so that's the class we created, to char star for the third argument. So we need to actually get the message which returns that char star value, and then this should work now. That should be the last of them. Except if you go back to the class definition and look at the append and the remove methods, you'll probably note that I've declared them to return a Boolean value, but don't actually return that Boolean value. So we will figure this out a little bit later on and fix it, but that's a one more problem, a logic error. Okay, so first order of business is echo on. Probably should make that the default setting. LED 5 on. And sure enough, that's worked. Usage. That looks like it's working. I think I didn't do this before, so LED 1 on. So we've got, yeah, invalid pin number should be 2 to 13. Let's try this. I have no idea what's going to happen, but I guess we'll find out. Yes, that's LED X on. I think also the echo wasn't working. Yeah, so the backspace was not working. So we still have a little bit of a problem here. In buff remove, and that's because we're not actually returning a value. And then the same will be here. Okay, so LED, so now it's working. So what was happening was we didn't specifically return our Boolean value, so we kind of just got a random value coming back, which probably was this 0. This 0 for the remove. But I don't know for sure. It's just random, and that's why we would be not having the echo work correctly. But in theory, if I said LED and then hit it one more time, that should be okay. If I hit it one more time, I should get the underflow message coming up, which is what would expect, because that's what's happening here. So if you're happy with the way it's working, you could comment these debug messages out, and I think I'll just leave them in this version. I might comment it out for later, but basically it's working as we'd expect. And so, yep, that's great. All right, so what I'm going to do next, I think, now that we have that, is I might tidy a few things up off camera, but probably not too much, maybe nothing. And what we'll do next, I think, is move on to doing some multi-Arduino communications or multi-device communications, and using the serial stuff. Okay, so let's get started with that. Alright, so a bit earlier I looked at a program like this which simply takes data from Serial and sends it to Serial 1 and vice versa, and we use that to sort of illustrate how we can interact with a Bluetooth module and get access to its rich command set and configure it and do lots of stuff with it. We can also use this in other ways. So I have here a Mega, and I'll explain why I'm using a Mega shortly, and I've got it connected to a GPS module. This GPS module uses Serial for its communications, and so there's 4 connections. There's a ground, power, and then there's a TX and RX, which is Serial, and that's what these 2 wires are connected to, TX and RX. I'll go into the little circuit in a little bit more detail, but just show another way that we can use this. Okay, now in this case we won't want echo to be turned on. Hopefully that'll be clear later on, but basically I'm going to use this with another program and we don't want its commands to be echoed back as per this case. So I'll just upload that. The right port, Mega. Yep, that was lucky. And if we activate the serial monitor, then we can start seeing the GPS, which doesn't have a signal yet, but it's starting to send its data to us. Now, where that's really interesting is we can actually use it with a different program and use that program to actually interact with the GPS through the Arduino. And the reason that's useful is because we can't connect this GPS directly to our PC unless we have some sort of an adapter, and the Arduino provides us that capability. Okay, so I'll just fire up the uBlocks console. This is a tool or a diagnostic tool that they provide that allows you to interact with their modules. It does require the ability to communicate with it through the COM port, and that's where the pass-through on the Arduino does come into play. So you can see once I've connected it, it's receiving that same data in that lower left-hand window, and it's already got a fix, which you can see in the latitude and longitude in the top right window. And also in the map, there's a little green icon on the right-hand side, which shows that basically in Fiji, which is where those photos were taken. As you can see, it's a lot of hard work and a nice location to record this segment of the video. And just in case you were wondering if I'm doxing myself or anything like that, I don't actually live in Fiji. That would be nice. It'd be nice to live there and have that view every day. But alas, I don't. It was just there for the video. Okay, so why am I using a Mega? Well, basically because it's got more than one serial port. Now the Uno that we were using previously, it does have a serial port here on pins 0 and 1. You can see they're labeled TX and RX, but they're actually used for something else. So let's just have a look at that. So this is the pinout diagram for the Uno. That's the ATmega 328P, which is the chip that we're putting all of our code onto. But there's also another little processor up here, and this is the gateway to the USB. And the way it works is that the TX and RX, the one and only serial port on this chip, is connected into this one, and this translates into USB for us. So we can't sort of really use this for communication with something else like a GPS and send the data to the PC. You kind of can if you upload no program. This is still sort of connected to that, so you can kind of act as a gateway by basically having this empty. But that sort of has a very limited use cases, and I won't go into that. So generally on the on the Uno, Serial is not generally available for us to use, except for that one scenario where I showed you earlier where we remoted into it from the tablet. And so that's highlighted by looking more closely at this section here where we can just see there's the one pin, and it's also a helpful note there connected to the ATmega. It means this one here, the 32U4, or it could be a 82U or 16U2, and that's used for programming communicating with it. So generally we can't sort of use that. So on the Mega, it has a lot more I/O, and as per the Uno, Serial is used, and that's these pins 0 and 1. So Serial is used for upload, and it's not available to us. But there are others available on pins 14 to 19. So I'll look at that a bit more closely. So if we zoom in on that section, we can see here that pins 0 and 1 are TX and RX, and they're used for connection to the AT Mega. Again, it means the 32U4 or whatever coprocessor is on here, and they're generally not available for us to use. If we extend down a little bit further and we look at these pins, then we can see that there's 3 more pairs. So serial 1, serial 2, serial 3. And that's what this program was using. It was using serial 1, and serial 1 is these pins down here, which are, what are they? Pins 18 and 19. That's these two. And so we're just relaying data between this serial and effectively the serial that comes out through the USB here. So the reason that's important is for when we actually start working on the game that I showed earlier, where we have 2 Arduinos talking to each other. So they'll use one of these serial ports, serial 1 in fact, serial 1, to communicate game information with each other. And then it'll also use this one, the serial 0 or the built-in serial port, to send debug messages, and I can also send control messages. And what I'll do is, when going through that program, I'll actually hook up a pass-through Mega like this one, so I can actually pretend to be sending game messages to it to control or to pretend that there's another game at the other end. And that's really useful for debugging. It's helpful to have these extra ports. The way we hook these up is we basically cross the wires. Now, that's not always the case with communications, but for serial it is. And the simplistic rule is that TX on one side connects to RX on the other side. And that can be seen here. So the green wire comes out of TX on this one, runs its way around here, and it connects to RX on this one. Similarly, the blue wire comes out of TX here, it runs its way around and connects to RX on the other side. And that's exactly how the game is set up. The other thing that we need to have is a common ground. I won't go into why, but you just, in this case, you just do. So we have to have those 3 connections. Okay, so let's have a look at the game. I was planning to develop it, but it's about 1,400 lines, so that's a bit long for this video. And plus, this is more about serial and how we can get 2 Arduinos to communicate with each other. So I'll focus more on the communications and build upon some of the stuff that we've used so far. Okay, so let's get stuck into that, shall we? I'll just plug it in. Okay, so we quickly looked at this earlier. As you can see, there's the game there with the board initialized. And the communications between the two is via serial port through this wire here, and that's connected to serial 1 on the Mega. So we'll look at the code briefly for how this works, but also look at how we can use the putty to sort of debug this. So the way it works is the 2 Megas are hooked together. There's 2 interfaces. The first one is the serial port through the USB connection, where we can enter commands like this to sort of see what's going on. So I can connect to one of those. Yep, so we can enter commands like this, help. We can show the board, which is currently showing nothing in particular, but if I click a few, not sure which one we are, but that'll do. Then I can see from memory what the board setting is. So it looks like, actually I'm not sure because they'll both be the same. I can also type in status. And so this is telling us who we are. So I'm the naught. So that would mean that I'm interacting with this one. And I can also do things like here I can't reset the game because that's disabled until the game is finished. But I can actually enter that through the command line and force a reset. Now the other thing that it's showing here is these messages. So OX : init and OX colon reset and a number. That's showing you a sample of what the commands are that's being sent through here between the two of them. And that's the type of commands we can see. So there's a reset. There's also a move command. I don't think that was being showed. Oh no, there it is, OX move. So when trying to make this program work, it is actually convenient to not try and have the program communicating with itself. It is convenient to sort of have the serial interface. Just bringing back this one, if I were to upload this, so I'm currently connected to COM5. Yep, COM5. The other option is COM16. So what I'll do is open up putty on COM16. There's our putty, and as before I can type in commands like that, and because I'm now using putty I want to turn the echo on, so that's that command. There's our help, status, board, so on. But if I upload this one, so this is to COM5, which is this serial monitor. So this serial pass-through is the same one that we used before. It's just taking the data from the USB connection serial and sending it to serial 1, which is causing it to go across this wire here, and then vice versa. Anything that's coming from the wire from the other Arduino is just being echoed back to the serial monitor. So that's what's going on here. And then this one, of course, is connected to the one that's actually got the noughts and crosses game on it. So I should be able to type in something like, and you can see that we've actually received that message. So that's gone through one of the Arduinos into the other one. So I just work out which one I am. So I'm the naught. So that's this Arduino here, and this one is running the null serial program because the screen is blank. Basically, we can tell that that's the right one. So I could issue a command here like that reset, and what I should see is the command that the game Arduino is sending to our pass-through one. So I send that reset, and we can see there's that message that's come through, and that's the command that it's sent. Now the reply to that is OX init, and we might say 1 and O, which I can't remember exactly, but I think that means that I want to go first, and I'll be an O, which means that I'm an X. I don't know if you can see that on the screen there, but it does say I am X, and it says waiting for the opponent. That means that the pass-through one is going to go first. So I can say something like OX move, and let's say I want to go to row 1, column 0. And sure enough, we get the O there. Now, if I click on this one, then I should get a move message from this one, which says 2, 2, because that's where I've moved to. And so I can just repeat this. Where should we go? 0, 0. And that's quite useful because we can do things like error handling. I mean, we don't really want the program to generate an invalid command, but we can force that through this sort of debugging type of console without having to hard code anything particular. And so you can see here it didn't handle it very well. Let's put the little circle over there, but it didn't crash. I guess that's the main thing. But it did recognize that it's invalid because it's actually waiting for a proper move. That's kind of handled it okay. So let's go 1, 1. Okay, so it's handled it, and now it's got a valid move, so it's my turn. So having the ability to use a little pass-through or putty is actually quite handy when you're debugging commands like this, because as you can see, we can have a rich interface which comes through the USB port, which is where the putty is at the moment, or we can tap into one of these other communications channels, which the programs will ultimately use to communicate to each other. So how does all that work? Oh, here's the code here. So it starts off pretty standard. There's a couple of serial.begins. There's a remote com.begin. So remote com is something that's defined up here to be serial 1. So wherever we see remote com, that means serial 1. That just gives me some flexibility that I can change the port if I wanted to whatever I need it to be. And now I was going to develop this in the video, but it's 1100 lines there, plus there's these other files, so I won't do that because it's just too much. But if that's something of interest to you to sort of see how it works in more detail, by all means drop a comment and let me know. Anyway, so there's other initialization here. And the important thing here is it's doing this check comms function, and it's taking a few parameters. So you can already get a clue that I'm reusing some code here to do the same process. And I'm passing it which serial device I want to use. So remember that's serial 1. And I'm passing this remote buffer, local buffer, and some of these other things. So this is the function here. So ignoring this one for a second, we're passing in a buffer, and as before, this is the exact same buffer that we created earlier. So you can see there's the clear, there's the getlen, there's the message, this is the append, there's the header file, and there's another file here which is basically generating a proxy for the graphics, so I can have a standard set of functions like get rotation, set rotation, which are attuned to the particular display. So that's not terribly important for this. It's more about the buffer, which we looked at earlier, and then what's going on here. The next thing is this rather curious function here, or parameter, I should say, this rather curious parameter here. And so what this is doing is, if you look at it sort of closely, it looks a little bit like a function call. And indeed, here it is here. And so what I'm doing is, in this check communications thing, when we get a new line character, I'm calling this function. And this function, which is the third parameter, is defined here. And so there is actually a function called process remote. And there it is. Oh, not that one. Process remote, which takes a single parameter being the buffer. Similarly, there's a function called process local. Which is this one. Again, it takes a single parameter being the buffer. And so this is where it's doing things like the tokenization that we looked at before. So there's the str toke. There's an array of tokens, and we're extracting them, and then we're doing this process, and that's where it's breaking out the commands to look for the help, the usage, the board, the status, the reset. So pretty much the commands that we were typing in here. Okay, so that's these commands are being processed by this function. And the way that works is that this is the name of the function, and it's passed this as a pointer. So this is another way of using a pointer. And then this is invoking the pointer to that function. So it's resolving the function or the pointer to call the appropriate function from here. And the function that gets called depends on which one we name here. The other part of this is it says that we're actually giving it a function that takes a single parameter, which is a reference to a buffer. So that's what this ampersand is. You notice I've used the ampersand here and I've used the ampersand here, and that's a way that we can pass a type of pointer to something. And in this case, we're passing the buffer in for the purpose of collecting the characters, or removing them as case of the backspace, or processing them. And then we pass that buffer to the function based upon which module we're looking at. And that is, do we want to process a command from here, or do we want to process a command from here? Then the last one is the echo. So basically, if we're echoing, then it'll echo the characters back, and whether we're echoing or not will depend upon whether it's the remote or the local. And so there's another parameter here that handles that. The rest of this stuff is just about playing the game. So there's a state machine which basically says whose turn is it, so it tracks a lot of that sort of stuff. So I won't go too much into that because there's no communications there, other than it uses this function here called send move to. Okay, so we've already looked briefly at the process local, which tokenizes the string. It tokenizes it based upon a space being the separator. The other function is the one that processes the OX based commands, of where there's an example just there. And so what that's doing is it's also doing tokenization. That's a little bit further up. Here we go. In this case, it's doing the tokenization by separating on the column. So our words that we'll get will be OX, confirming it, 0, and an X in that case. So we get four words or 4 tokens. But the function is basically the same, except for this difference here. And then it uses this process remote tokens to work out what to do. And that should be just here. Yes, it is. And so basically what this is doing is it's checking to see if we've got a valid command. So is it an OX command? And then if it is an OX command, then it'll look for reset init or one of the other commands that it receive. And then based upon what command it is, it's actually doing the processing in here. So here is the move command. It's extracting the tokens because there's a move command there. So that's the row and the column. So we're getting the row and the column out. And then it's just updating this game board here, which is this representation down here. So that's essentially the communications. It's very similar to what we've looked at earlier with the simple program that turned the LEDs on, but it's a bit more richer because we have the 2 channels of communication, being through the USB port or the interaction between the 2 modules, and the command set is a bit richer and appropriate to what it is that we're doing here. There's some more some helper functions which generate the messages that are sent to the other side. Nothing really special there. This send message to remote function. Pretty much is just a print statement. So it sends whatever the message is that was sent or received. Sorry, I should look at this one. So it sends whatever message needs to send to the other side. And then based upon this parameter here, it works out whether it needs to output a new line or not. And then this start of line is just something that says, do we want to output this debug message or not? We are seeing there. Now there's a variant, that's this one. So if it's being passed along, then we basically want to do the same thing, but because we take 2 different types of parameters, being a string or a number, then it will have two different variants. They basically do the same thing, but this is just to do with handling the different data type. Okay, so I think that's pretty much all I want to cover in this set of videos. Hopefully that's been helpful. Let me know what you think in the comments. Also, don't forget to like and subscribe. And I'll just close it off here. Alrighty, well, thanks for watching. Again, hopefully that was useful. Don't forget to like the video, subscribe to my channel, and leave a comment if there's something you'd like to see or something you found confusing. By all means, do that. Also, look for me on social media. I'm very commonly on Reddit and other forms of social media. So look for me there, and see you next time on All About Arduino. Bye for now.